Okay, for our Unit 5 test, there are a few reference materials we'll have to know how to use. We have our activity series, and whenever we look at our activity series, we have our activity series for the metals right over here. And it shows the increasing activity traveling up. So these are going to be your strongest elements here at the top. And then down here at the bottom is where you're going to find the weakest elements. And we use these for single replacement reactions to see if a metal is strong enough to replace another one. So if I wanted to find out, is calcium strong enough to replace zinc? Yes, it is, because it's above it on our table here. So we are only going to use our activity series for single replacement reactions. And we'll review what those are as we continue to look at some of the reactions below. The other reference material you need to be able to use is our solubility chart. And we find it on the same page. Our solubility chart, it's here in the middle. And it tells us if our substances are soluble in water. So this whole top part are where we have soluble compounds. They will dissolve. And then down here below we have insoluble. They will not dissolve. So if we're going to be labeling these substances on our equations, if it does dissolve, we say it's aqueous, and we put AQ, it dissolves in water. If it is insoluble, that means that it will not dissolve, and it will form what we call a precipitate. And the way that we show that a precipitate is being formed is with a down arrow. So whenever we write a chemical reaction and we want to show that that is a precipitate being formed, we'll draw just a down arrow after the chemical substance. And we will use this type of chart to look up information for our double replacement reactions. That's whenever everything involved is a compound. You also should be familiar with our diatomic elements. When we look at our periodic table, we find them all in a certain location. Sometimes we call them the diatomic 7, because if you start at number 7 right here, and you come over and you make a 7, it's going to get all of these elements right here. So we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. But that's only 6 elements, so in order to make it a total of 7, we add in hydrogen. Those are the elements that are going to be found in 2s. And the periodic table in our classroom has the 2s on there, so you can always look at that if you need to. But our 7 diatomic elements, we came up with a little phrase to help us remember them also. So if you want to remember, you can say hi. So you've got hydrogen and iodine. And the person you're saying hi to, his name is a little strange. His name is Broncliffe. So you get your bromine, oxygen, nitrogen, chlorine, and fluorine. They're all diatomic, meaning 2. Okay. Now, for the rest of these, we're going to use those resources to help us do 3 different things. First of all, we're going to complete the chemical reaction. We'll actually write out what it looks like. Then we are going to balance that chemical reaction if it will happen. And then at the end, we will label what type of reaction that reaction is. So we have 3 different things that we're going to be looking at. And we'll follow that color coding so that you understand each different step. So the first reaction says that propane, C4H10, undergoes complete combustion. So we know that it's going to go through combustion. That'll give us the type of reaction. And it says it will produce carbon dioxide and water. So we'll start out just writing our formula here for propane, C4H10. And you have to remember that if you have something going through combustion, it's burning, that means that it has to react with oxygen. And I would go ahead and leave spaces so that you can fill in coefficients. So those are your reactants. Draw your yield arrow. And then we're going to write what it forms or produces. It says it's going to produce carbon dioxide, carbon and 2 oxygens, plus water, H2O. So that's the first step, completing our chemical reaction. Now we want to balance. So whenever you want to balance a combustion reaction, you're looking at 3 different elements on each side, carbon, hydrogen, and oxygen. And we'll just start by listing how many we have of each. Carbon, we're starting out with 4. Hydrogen, we're starting out with 10. And oxygen, we're starting out with 2. On the other side of our reaction, let's list them in the same order. Carbon, we start out with 1. Hydrogen over here, we're going to have 2. And you have to be careful with oxygen because it's split up here. So we'll have 2 oxygens here, only 1 over here. So 2 plus 1 gives us 3. And we want to balance the carbon and hydrogen first, since the oxygen is split up. So if we have 4 carbons over here on the reactant side, to get 4 on the product side, we'll just put a 4 in front of carbon dioxide. That changes that to a 4. Go ahead and balance hydrogen. If we have 10, then in order to get 10 on this side, we need to multiply it by 5. So the 5 times 2 now gives us 10. Once you have carbon and hydrogen balanced, then you can see what it does to the oxygens. So you have 4 times 2 for a total of 8, plus 5 times 1, or 5 more. So you end up with 13 oxygens on the product side. Now we cannot multiply 2 by a whole number and get 13 because it's an odd number. So we talked about in class that whenever this value here ends up being odd, what we end up having to do is take this number, go ahead and place it as the coefficient for oxygen, but then you have to take every other coefficient, this would have been a 1, and you have to double it. So we'll double that one, and that one. So our coefficient list that we end up with would be 2, 13, 8, and 10. Remember, that's only if you have an odd number, you have to do that for the oxygens. If this had been a 12 instead, then we could have just put a 6 there to make 12 oxygens. But it was an odd number, so we had to follow through with that process. Now, the last step here is to give our type of reaction. And they actually told us in the problem that this was combustion. And the way that, if it didn't say that, if we just had to figure out if it was combustion, remember your clues are always that it's going to react with oxygen, and it's going to form either CO or CO2, depending on if it's incomplete or complete. And then it will also form water. You have to have all 3 of those along with your fuel for us to label it as combustion. Okay. For number 2, we have 2 different chemicals we're starting out with. We're going to have barium nitrate, and it's poured into a solution of potassium chloride. So if we're going to write down formulas for those are compounds. We have to figure out what their charges are. So we go and we look at our periodic table. And recall that if it's in this first column, it's +1, +2, +3. This one's a question mark. -3, -2, -1, and 0. Here in the middle, it'll be a positive question mark. And then we had our handful that we wrote our charges on here in the center for our transition metals. Now you get to use your labeled periodic table. You don't have to have those memorized. So whenever we want barium, we just look that up on our table and we see it has a +2 value. Nitrate, when you see 8 or ite, that should be your clue that you have a polyatomic ion on your hands. So anytime it's 8 or ite, you're going to go look it up on this chart. So we have nitrate right here, and we can see its formula and charge. It's NO3, and the charge is a -1. We just don't write the ones. So we'll go ahead and label that nitrate would be a -1. So if I write my formula for that, for every barium, I'm going to have 2 of these nitrates paired with it in order to get those to add up to equal 0. So I'm going to put this in parentheses and put the 2 outside. That's how you show you have more than one polyatomic ion. We're going to do the same thing with potassium chloride. Potassium, we look it up, it's a +1. Chlorine is a -1. Remember, it's "ide" at the end. It's just whatever element on the table sounds like it. So chloride is chlorine. So if it's a +1, -1, you have just one of each, KCl. Now, you should recognize that if you start with 2 compounds, you're going to have a double replacement reaction. And what that means is that whatever you have as a metal on this side is going to pair up with whatever's non-metal out here. So your outer elements will come together to form one of your products, and then we'll see the same thing. The inner parts will pair up to make your other product. So let's see what products could be forming here. If we start with the outside, we have barium and chlorine. And if we looked at our charges, barium was a +2, chlorine's a -1, so we have to have 2 of them to balance our charges. And then our other potential product, we'll take the middle parts. We always have to write the metal first, though. So that would be our potassium and then our nitrate. And let's look at our charges. Potassium's a +1, nitrate's a -1. So I actually should have written that a little bit closer together. It would have just been KNO3. Now you should recognize, and we can go ahead and label it, that because we have all compounds here, this would be a double replacement reaction. We have 2 compounds are separating, switching around, 2 replacements are happening. And when you have a double replacement reaction, we have to look at our solubility chart to see if it can even occur. So we're going to look at our negative ions. We've got chlorine paired up with barium, and then we have nitrate with our potassium. So let's go and take a look at our solubility chart. So we have chlorine. Chlorine's right here. Chlorine will be soluble unless it's with one of these 3 things, but barium is not one of those. So that means that it will be aqueous. Our other substance was nitrate. It's always soluble. It didn't matter if it was with potassium or not. There are no exceptions. So both of our products that could form are going to dissolve in water. So after our formulas here, we're actually going to put a little AQ that's going to tell us that that will dissolve. AQ and AQ. Now, one of our rules is that for a double replacement reaction to take place, you have to have a precipitate form. You have to have something be insoluble and found in that bottom portion of the chart. And since neither one of these were precipitate, that means this reaction cannot happen. So what you do in that case is you draw a line through your potential products, and then you write no reaction. And we just abbreviate reaction RXN. Now, since the reaction won't happen, you don't have to take your time to balance. You are done with that one. Okay, for our next reaction, we have aqueous aluminum chloride, and it attempts to react with bromine. So that's telling us what we're adding together. We're going to have aluminum chloride, and it's going to react with bromine. Now let's think about it real quick. We just got our symbols for them. This is a compound, though, aluminum chloride. That means you go to your table and you look up your charges. So we've got aluminum, which is a +3, and you've got chlorine, which is a -1. So if we write those charges up here, that'll help us figure out what it'll look like. +3, -1. If those have to add up to equal 0, we've got to multiply this guy here by 3. Now our charges all reduce to 0. When you have a single element like bromine, remember the only thing you have to worry about is it one of these 7 diatomic elements? If we look here, bromine is in fact diatomic, so that means by itself here, it will have a little 2. They pair up. So it's trying to form aluminum bromide and chlorine. So let's go ahead and take a look and see if this reaction can even occur. You should recognize that since you have an element and a compound, we're going to be trying to have a single replacement reaction. So what that means is that we have to look at our activity series and see if our lone element is strong enough. This element right here, is it strong enough to replace the element that's like it in the compound? So bromine's a nonmetal on the right-hand side of our table. So see if it will replace chlorine, which is also a nonmetal on the right-hand side. Now, if you look at your activity series, you will notice that it does not include nonmetals. It only has metals and hydrogen. So since we don't see that on that chart, we actually go and look at our periodic table. The only elements that are nonmetals that we see having to look at the activity series for are going to be these four right here: fluorine, chlorine, bromine, and iodine. So is bromine down here strong enough to replace chlorine? It follows the same rule where it's strongest up at the top and weakest down here at the bottom. So bromine is not stronger than chlorine. It can't kick it out and take its place. So that means that because bromine is weaker, this is going to be no reaction. And you don't even have to write out the potential products. It won't happen. So of course there is no balancing to do on this one. In our next reaction, we have iron 3 oxide, and it says it decomposes. So that means after you write your formula for iron 3 oxide, then you'll go ahead and put your yields arrow. And it says it decomposes into its elements of iron and oxygen. So you need to look up your symbols for iron, Fe, and oxygen, O. And you need to think about, are these diatomic? Are they on our list over here? And if we have Fe, we check. Nope. We look up O. Yes, oxygen is diatomic. So that'll have a little O there. Now going back to our iron 3 oxide, this will need to find the charges to write our formula. So iron has a charge of +3. We get that from the Roman numeral right there. Oxide means we look up oxygen, and oxygen over here is going to have a charge of -2. Anytime you have a 3 and a 2, remember you have to work to make them both equal 6. That's the smallest number they could both equal. We also talked about how you could basically just make those numbers switch places to become the subscripts. So we would have Fe2O3. So you have a -6 and a +6, and they cancel each other out. So we do need to go ahead and balance this. So whenever you're listing your elements, we separate our reactants and products. We have Fe and we have O. We'll list them in the same order over here. Oh, and I made a mistake. I was just copying everything. We only have one iron on this side. And then oxygen over here, we're going to have a 2. So look and see what you have that does not match up. You might see that the irons don't match, so in order to get this side equal, we just need to multiply it times 2. Okay. Then you look at your oxygens. Again, we have a 3 and a 2. So you have to do the same thing as we did with the charges. They both have to equal 6. So what can you multiply 3 by to get 6? You multiply it times 2. So that'll give us 6 oxygens over here. But take a look. It also changes how many irons we have. We started out with 2, but if you multiply it by 2, now it's 4. So let's finish balancing the oxygens. We got 6 on this side. So to get 6 over here, we need to multiply it times 3. Now we need to go back and fix the iron, and this happens sometimes. Sometimes you'll write down a number, and then you'll change something, and it makes it have to go back and change something else. So instead of writing a 2 there, we can just write a 4, and now everything is balanced. So our coefficients are 2, 4, and 3. And our type of reaction, it says in the problem, it says that it decomposes. But also we see we start with one reactant and it breaks apart into its individual elements. So that's how you can look at a reaction and recognize that it will be decomposition. You start with only one reactant and it gets pulled apart. It decomposes. For our next reaction, we're going to be starting out with a piece of sodium, and it's placed in a solution of cobalt-3 sulfate. So the way it's worded tells us we're going to take that and add it to that. So a piece of sodium, Na. It's an element, so think about, is it one of those 7 diatomics? It's not, so it does not need a 2. And we've got cobalt-3 sulfate. So we need a charge on these things. We've got +3. And then again, we see that 8. So we go to our list and we look for sulfate. We've got sulfate. SO4. The charge is a -2. So if we want our charges to balance, again, we need to get 6. So in order to get a +6, we multiply that times 2. Sulfate, we said, was SO4, so we keep it SO4. We just put it in parentheses, and we multiply it times 3. You can also see that we're taking those charges and just kind of making them swap places. Now, we should recognize you've got a single element by itself, and it's reacting with a compound. So that means we're going to have a single replacement reaction, a single element trying to replace part of a compound. And before you even take the time to write the products that could form, let's just see if it'll happen. This is when we go and use our activity series. We're trying to see, is sodium strong enough to replace the element that's like it here? So sodium's a metal on the left side of our table, so can it replace the metal in the compound? So is sodium stronger than cobalt? So let's go look. Is sodium stronger than cobalt? It's above it on the list, so yes, it is. So that means our reaction will take place. The sodium will kick out cobalt, so now cobalt's going to be out here all alone. We don't carry over the subscript. It's not diatomic, so it doesn't need a 2. And now our sodium will take its place and be paired up with our sulfate. What we have to worry about now are the charges. We know sulfate's a -2. We just need to look up and see what the charge for our sodium is. So when we go and look at our table, sodium's here in this first column, so it'll be a +1. So if you have a +1 and a -2, we need to multiply that times 2 to get that product to form. So we have our reaction here. We are now going to need to balance. So I'm going to get that out of our way here. And we're going to need to list our elements that we have. And you can go through this process in your head. You don't have to list everything that we have. So some students like to kind of have everything there. Makes it a little bit easier to see what's going on. So we're going to list Na, C, and SO4 and how many we have of each. So we're going to have sodium, we've got 1, cobalt, we have 2, and go ahead and keep sulfate all together. It's on both sides, so keep it as one single thing. We have 3 of those. So list them in the same order so we can compare. Sodium, we look over here, we'll have 2. Cobalt, we've got 1. Sulfate, it's not in parentheses, so that means that there's only 1 of them. So look to see what does not match. Sodium is the first thing I notice. So to get it to balance, we put a 2. And now they match. Cobalt also does not match. We got a 2 and a 1, so we'll put a 2. And now we have our sulfate. You've got 3 over here, so we need to take that and multiply it times 3. But you got to be careful because when you put that 3 there, look and see what it did. We've got 3 times 2, or now we have 6 sodiums. So we go back over here to sodium. Instead of a 2, we need to make it a 6. So now we have 6 sodiums, 2 cobalts, 3 sulfates on every side. If you have a blank left over, it's going to be a 1 whenever you write your coefficient list. Those are the coefficients that would balance that chemical reaction. And then it is going to be a single replacement. Okay, a couple more here. For number 6, we have liquid mercury, and it's going to be reacting with solid iodine. So mercury and iodine. Mercury symbol is Hg, iodine is I. Since they're single elements, we do have to check and see if they're diatomic. So you would look on your table or remember your little list and look to see. Is mercury on here? Hg? No. Is iodine? Yes, it is. So Hg does not need a 2, but our I does. So they're reacted, resulting in, that's our arrow, mercury to iodide. So we've got Hg and I. We just need to look up charges to see how many of each we need. So mercury, it says that the charge is at 2. Iodide is just going to be iodine on our table. Remember, IDE means that it's on our table here. So we go and we look up I. Its charge is a -1. So we want those charges to all add up to equal 0. So we need to multiply that one by a 2. If we need to balance, we can list what we have on each side. We've got Hg equal to 1, I equal to 2. Hg, we have 1, I, there are 2. Everything already balances. So if we were to write coefficients in those blanks, it would be 1, 1, 1. A type of reaction when you take two things and put them together and you make only one product on the right-hand side, that will be an addition reaction. Okay, last one here. We have a solution of lithium phosphate, and it's mixed with a solution of barium nitrate. So these two things are going to be added together. When you have compounds, you need to know the charges for the elements involved. So when we look up lithium, it's in the first column. When you look up barium, it's in the second column. Those elements are easy to find. The second parts here, you'll notice, end with 8. That means they're polyatomic ions. So we go and we find them. We've got phosphate right here, and nitrate, which we've already used. So whenever we go to label those, we just copy down the charges. Our phosphate's a -3, our nitrate's a -1. So we'll leave a little line so that we can balance. And think about what you need to multiply that by so it cancels. You'll need to multiply it times 3. And our formula for a single phosphate was PO4. That's what it said on our paper. So we're just going to put PO4 since we just need one. And it's mixed with barium. And then to get our charges to balance, we need to multiply this times 2. So we'll put our NO3 in parentheses. A single nitrate was NO3 minus. And we'll put a little 2 to show that we need to multiply it by 2. And it says it will form the compounds lithium nitrate and barium phosphate. So we could have looked at this and noticed that with two compounds, that these are going to pair up on the outside, and on the inside, these would pair up. But they went ahead and told us what our products are going to be. So we have a lithium nitrate. Just take the charges we already looked up and copy them down here. And then a barium phosphate. So +1, -1, that means you need just one of each. I'm actually going to leave a little bit of space because we're going to need to find out if it's going to be a precipitate or if it's going to be aqueous, and we're going to need to be able to label that. The other product, we've got a 2 and a 3, so those are going to swap places. We get Ba3, and then PO4 too. So since they are all compounds, this will be a double replacement reaction. And that means that we have to go and look at our solubility chart to see if it will even take place, or if it'll be no reaction. So let's go and take a look. We've got lithium nitrate. So we're looking at the nitrate, NO3. There are no exceptions, so anything with nitrate will be soluble. It will dissolve in water. So that won't help us with our reaction. If the other one's also aqueous, it'll be no reaction. So let's find out. We've got PO4 paired up with barium. So we look for PO4 on our list. PO4 is going to be right down here. So this will be a precipitate as long as barium's not an exception. If we look, we've got ammonium or the alkali metals, which is the first group on our periodic table. Sodium, lithium, potassium, those. So barium's not in that group. That means that our phosphate ion, the compound, will be insoluble. Put a little down arrow. That's our precipitate that tells us this reaction will, in fact, take place. So let's go ahead and balance. When you have polyatomic ions on both sides, remember, you get to keep those together and look at them like they're a single item. So lithium, we're going to start with 3. Phosphate, since it's on both sides, we'll keep it together, has only 1. Barium is 1. And we'll keep nitrate together. We look at the little 2 out here to see how many. Write them in the same order. Lithium, we have 1. Phosphate, we look over here, there's 2. Barium, we have 3. And nitrate, there's only 1. Right there. So look for anything that does not match. Our lithium does not match. We have a 3 and a 1. So let's put a 3. It gives us 3 lithiums, but it also multiplies over here to give us 3 nitrates. So you might go with the nitrate next. We just changed that to a 3, but that's a 2. Okay? So whenever you have a 2 and a 3, remember we need to get 6. So what do you multiply this by to get 6? We multiply it times 3. And then over here, we already had a 3, so let's cross it out and let's just change it to a 6. And look to see what that did to our lithiums. Now we have 6 of them. So now over here, lithium, it doesn't match anymore. We need to have 6, so we need to just multiply it times 2. So now that matches, and if we look, that also gave us 2 phosphates. So we have a 6, a 2, and I messed up. I did not change this whenever I got 3 bariums here. Okay. We should always remember if we change one of the substances, be sure we change the other. I goof sometimes too. And then we got 6 on there. So this very last one that we did not need a coefficient for, we just fill in with a 1. So our coefficients are 2, 3, 6, and 1. Now on your test, it will be multiple choice and matching. So you won't have to carry out every single step of this for every single question. But you will have to be able to figure out what type of reaction it is. You will have to be able to identify correctly written skeleton equations. That's what's in green. And then you will also have to balance chemical equations. And that's the part that we did in blue.